Hello everyone, I'm Prakash Vanga, overall 13 years of extensive experience specializing in AWS Cloud Engineer and Identity Access Management. Currently serving as an AWS Data Engineer, designing and implementing scalable and secure data pipelines leveraging AWS services. I'm really excited to be here to talk about something that at the intersection of AI, cloud infrastructure, and real-world business impact. Using cloud native AI to fight financial fraud in real time and doing it reliable. Today, financial institutions face critical challenging detection, sophisticated fraud pattern across billions of digital transactions while maintaining system reliability and performance. In this session, we dive into how site reliability engineers or SRE empower financial institutions to build cloud native AI systems that detect fraud at scale without compromising speed, availability, user trust. We will explore how to architecture infrastructure capable of sub-second responses time, handle massive transactions volume, and still hold the gold standard of 99.9% uptime. This is about more than just stopping fraud. It's about building resilient, intelligent systems that form the backbone of modern financial security. Going to next slide. The challenge faced in this is mainly speed, scale, and security. Let's start with the problem. Today, financial systems processing billions of transactions daily, exposing them to constant, sophisticated fraud attempts. Legacy systems, which analyze data in batches, hours after transaction happened, simply don't work anymore. The challenge is huge. Detect fraud in real time across massive volumes while keeping latency under a second and blocking increasingly advanced attacks. For SRE, site reliability engineer, this means balancing performance, scalability, and security all at once. Going to next slide. Our experience from batch to streaming mentioning the architectural evolution. We started with a traditional batch processing system where analyzing data happened hours after transaction happens. That delay led to a lot of false positives and frustrated customers. To fix this, we transitioned to a streaming architecture. This was a big shift. We introduced Kafka Stream to process events in a real time, ensuring data flows continuously instead of in chunks. We added feature store to provide low latency access to historical data, giving our models the context they need instantly. This gave us real time insights and fraud detection that keeps us the modern threats. And we moved to microservice based model surveying, enabling real time inference with auto scaling so we can meet demand without sacrificing speed or reliability. Going to next slide, let us see the resiliency patterns for AI systems. AI systems bring new kinds of failure modes that traditional SRE method sometimes they return results too slowly. To handle these, we adopted specialized resilience patterns. We use circuit breakers to detect when models are overwhelmed, falling back to similar rule-based system to keep transactions flowing and avoiding cascading failures. We built graceful degradation paths where critical fraud checks continues even if deeper analysis needs to be passed during peak loads. And with automated canary analysis, we deployed new models to just a small portion of traffic. This let us monitor metrics like latency and false positives before a full rollout, reducing risk while improving quality. Going to next slide, specialized observability for ML systems. Traditional monitoring tools weren't enough for our AI fraud detection systems. They simply couldn't capture the complexity of model behavior or connect technical issues to business impact. We need to see how our AI models were performing and how that performance affected the business. So we built a specialized observability stack focused on model performance, data quality, and business relevance. We now track inference latency, prediction confidence, and compute usages across different model versions. We monitor data drift by detecting changes in statistical properties of input features so we know when real world transactions start to differ from training data. With explainability tools, we visualize why a transaction was flagged. This is a key for both debugging and gaining stakeholder trust. And finally, we correlated technical metrics with business outcomes like fraud, losses, or customer friction. So we are not just monitoring systems, we are tracking what actually matters. Going to next slide. Then we have service level objectives that balance security and experience. Setting service level objectives for fraud detection isn't just about uptime, it's about balancing multiple, often completing goals, security accuracy, fast approvals, and a smooth user experience. Traditionally, service level objectives focused only on availability, but that wasn't enough. So, we built a multi-dimensional service level objectives framework that combines both technical metrics and business impact. We track availability at 99.9% while keeping detection latency under 200 milliseconds for a seamless experience. To ensure quality, we aim for a false positive rate below 0.5 percentage and a fraud detection rate above 98 percentage. And to maintain trust, we required 100% explainability with clear reason codes for every decisions. This framework helps us to make smart trade-offs when we need to balance depth of analysis with real-time performance. Going to next slide. Chaos engineering for fraud systems. Fraud detection is a high stake environment. Failures he can lead to immediate financial loss. So traditionally, chaos engineering, which often involves breaking things in production, instead we designed a specialized approach that safe and controlled. We run chaos experiments in replica environments that mirror production using synthetic transactions data to stimulate both normal and fraudulent behavior. Each experiment is hypothesis driven, targeting specific failure modes, and most importantly, evaluate that degradation paths work, failure triggers correctly, and automatic recovery mechanisms do what they are supposed to do. This way, we gain the confidence of chaos testing without risking real money or user trust. Going to next slide. By applying SRE principle tailored specifically for AI-driven fraud detections, we saw major gain across both technical and business dimensions. The biggest win was a 78% reduction in detection time, which let us intercept fraud before transactions were completely preventing loss instead of trying to recover it later. We also cut false positives at by 63 percentage, which directly improved customer satisfaction. Fewer legitimate transactions were wrongly flagged. Few users experienced delays. At the system level, we maintained 99.99% availability, ensuring constant production without downtime. And finally, we achieved a 42% cost reduction efficient infrastructure. Going to next slide. In financial services, we are bound by strict regulations, which can clash with the fast moving, iterative nature of tech. To balance both, our SRE team built specialized workflow that supports continuous compliance without slowing down innovation. We translate regularity requirements into technical controls using infrastructure as a code to ensure every deployment is worked repeatedly and immutable. We also established a robust models governance framework, document training data, model logics, and how each ties back to a business need. Lastly, we implemented automated audit trails, logging every system change in detail. This allows to reconstruct systems state at any time, ensuring traceability and audit readiness at all times. Going to next. Building a reliable AI fraud detection systems isn't just about adding more power, it's about thoughtful architecture. Our blueprint focused on decoupling components. So if one fails, it doesn't bring the whole system down. We built in redundancy and ensure a full observability not just for technical metrics, but for business impact too. We break the system into reliable domains, each with its own scaling logics. This given us flexibility, especially when deploying new ML models, which often have unpredictable demands. At the foundation, we use scalable cloud infrastructure with multi-region failover. Our data layers uses resilience event stream from guarantee delivered. The model layer is isolated with the smart loading balancing, and finally, the observable layer gives us end-to-end insight across system health model behavior. Going to next slide. AI fraud detection systems can be seen as risky and complex, but with the right SRE practice, they become a competitive advantage. When reliability is built into a foundation, organization can deploy more sophisticated models faster with greater confidence and lower operational overhead. And this value doesn't stop at fraud prevention. The same infrastructure can support personalization, risk scoring, or market analytics, create a multiplier effect across the business. To get there, we recommend a three steps approach. Assess current capabilities. So identify reliability gaps and performance bottleneck using SRE principle. Building foundational patterns. Before scaling, implement key patterns like circuit breakers and observability. Measure business impact. Align technical reliability with outcomes like reduce fraud losses and better customer experience. By doing this, we turn reliability into not just by a technical goal, but a business strategy. Finally, thank you. Thank you all for your time. If you are working on fraud detection AI system, just trying to make your systems more reliable, I would love to connect. Let's keep building systems that are not only smart, but also strong, fast, and trustworthy. Thank you.